So welcome to uh, preparation of IIT JAM Real Analysis Lecture 2. So in this session, we will cover the differentiation and the integration portion. So in our last lecture, uh, we have seen up until continuity. So today it's differentiation and integration. So before starting off with differentiation and integration, it's um, it's very important that you go through previous year question papers and see a pattern of the problems that comes from differentiation and integration. Okay, so first we will talk about that type of patterns, and then we will discuss some of the key theorems and corollaries from the differentiation and integration portion. Okay, so let's get right into it. So in real analysis, whenever we have functions from a subset of R to R, then we know what is the definition of differentiation. Definition of differentiation, derivative, and we also know that what is the geometric significance behind that. Okay, so if you look at, so this the first half we are actually going to talk about differentiation in R. So if you look at previous year questions from differentiations, there are practically three key areas that problems actually come. So the first thing is mean value theorem. Mean value theorem. Second is the Taylor series, and third is the Darbox theorem. So these are the main three areas where questions from differentiation are specifically targeted. Now, there are questions that are interlinked. Okay, so what do I mean by interlinked questions? So there will be questions. Interlinked means that these questions will consist of all these three things: continuous functions, differentiable functions, and integrable functions. Okay, so one of those things are, if you have looked around previous year questions, it's something like this: that limit n tends to infinity, some 1 by n square integration. There are two functions given, let's say phi1 x, phi2 x, some if t dt. It's like this. So what will happen to this limit? Okay, so these type of questions actually takes on all these three things. So we will see in the, whenever we will be discussing on integration, we will see that what to do when we take, suppose this was my f. So let's say my f of x is phi1 x, phi2 of x, f of t dt, then what my f prime of x will be. Because sometimes that's all you need to know in order to apply L'Hospital's and rules. Okay, so then let's start in the derivative portion. Let us start with Let us start with the mean value theorem. So the statement of mean value theorem is not that difficult to understand, but it is the applications of those that you need to watch out for. So before going into mean value theorem, the very specific case of mean value theorem is the Rolle's theorem. So let's start with Rolle's theorem. Okay, so what does this theorem tells us? It says that, so whenever I write I, it means that it is a closed and bounded interval. Okay, so I is always a closed and bounded interval. So from, if I take a function from I to R, okay, and this function is continuous, and if is differentiable at I interior. So that means derivative exists. So what does this mean? This implies that if prime exists at every point of A comma B. Okay, so if this happens and f of A equals to f of B equals to 0, then there exists at least one point C belongs to, this is important actually. C is, we are not taking the endpoint because we have already taken the endpoints to be equals to 0, such that f prime C is 0. So what does Rolle's theorem geometrically tells us? So this is Rolle's theorem is something that is very much connected with continuity. Okay, so the fact is that since it's a closed and bounded interval A comma B, and since it is continuous, okay, so in any closed and bounded interval is practically a compact set in R, and if you take any continuous function, then over a compact set it always attains its supremum and infimum. It always attains both. Okay, so suppose then what might be the possibilities of these type of functions? So if f of A is and f of B is are 0, then one might happen that it might be either this, so this is one type, or like this, or it can be like this. So these are the types of patterns. Like I'm trying to maintain the fact that it has, so in this case it has, one has maxima, minima, or it both attains maxima and minima. Okay, so when f of A and f of B are 0 and there are no points that the function takes which are below 0, that means f of A and f of B are the minimum points. So these are the facts. So now what happens is, what Rolle's theorem tells you is that since it attains a maximum, minimum, so then there exists at least one point where the slope is actually 0. So that's what geometrically Rolle's theorem, that's what geometrically Rolle's theorem tells you. Okay, so slope is actually 0 at some point, and that is precisely when we say that f prime of C is 0, because the derivative at a point is just a slope. Now Rolle's theorem is nothing but the nothing but a specialization of the mean value theorem. So mean value theorem is kind of very important because by using mean value theorem, it's various problems can be solved. So it's exactly like that. If from I to R it is continuous, this is given, and if has a derivative in the open interval a comma b. All right. So then there exists a point C in a comma b such that f of b minus f of a by b minus a is equals to f prime c. So that is what mean value theorem tells you. Okay. So now, as you can see, that the Rolle's theorem is nothing but the specialization of mean value theorem, because in Rolle's theorem you take f of a equals to f of b equals to 0. So if you just put that in mean value theorem, then you see that there exists a point C such that f prime of c is equals to 0. Now, how do you apply mean value theorem? So there are various types of problems. So then let me kind of try to type of MVT problem. Okay. So one of the type of MVT problems are to establish critical points. Okay. So critical point means, so how do you, if you recall in your plus 2 level, how did you compute critical points? You took f prime of x and saw when f prime of x is 0. Okay. So then it falls under the mean value theorem criteria. Secondly, it is interesting when f has continuous derivatives. So whenever f has continuous derivatives, that means that derivatives are itself continuous. Okay. So in this type of scenarios, you should always look for an application of both IVT, intermediate value theorem, and MVT. Okay. And one of the usage of mean value theorem pattern problem is something like this, that if the derivative is bounded in a comma b, then f is uniformly continuous. Okay. So so one of the things is that bounded derivative implies Lipschitz. Okay, because if you look at this, then it is of this form. So this is kind of when you have a bounded derivative scenario. So if you just take mod xy here, then you will get the Lipschitz function. So it's a bit vague, but I am not going into too much problem solving discussion in today's session. But these are some of the types of MVT problems that you might look for. So the difficult portion comes when IVT and MVT, they are both added. So in our upcoming sessions, we will solve some of the IIT JAM problems, and there I will try to make sure that um, we will see that how these theories are actually taking place in problems. But by that time, it's advisable that you try to hit only these areas by solving some of the exercise problems from Rudin or Bartley Sherbert or whatever the books that you know as standard books. So after mean value theorem, one of the things that are very interesting is the Darbox theorem. Okay, so what Darbox theorem actually gives you, it gives you an analogous to intermediate value theorem in derivative. So this is Darbox theorem. So what does it tell us? So the first thing that you will see here, which is different from mean value theorem and Rolle's theorem, is that if let f be a differentiable function on the entire closed interval a comma. So whenever you see a problem which is given like this, that f is differentiable on closed interval a comma b, the first thing you should check is that does Darbox theorem hold here? Okay, so because this is one of those unique theorems where you consider the differentiability in the entire closed and bounded interval. So and if k is between f prime a and f prime b, then there exists at least one point c in a comma b such that f prime c is equals to k. So this is the reason that it's also called as the analogous of intermediate value theorem for differentiable functions. Because in intermediate value theorem for continuity, you actually do this exactly. Okay, like if it is there, then one of the things of intermediate value theorem is that if it is less than 0 or greater than 0, then there is at least one point which is at that point it is 0. So Darbox theorem is something that is analogous, but now it's on differentiability. Okay, so apart from these, some of the old school remarks that might help you. So in sequences of any sort involving x as variable, so increasing or decreasing can be understood from first order derivative test. Okay, so why is this remark? So the fact is, if it is differentiable, then f prime of x greater than or equals to 0, it implies monotonically increasing. And less than equals to 0, it implies monotonically decreasing. So whenever, suppose there might be questions like these. So let's say if I give you a function f of x, like x to the power 5 plus x cube plus x plus 1. Okay, so now if you take f prime of x, this is, as you can see, this is all positive. right? 3x square plus 1. So f prime of x, this is all positive, all right? So that implies that if this function is defined from R to R and it is increasing, it is strictly increasing. Okay, so because if it is strictly greater than 0, then it's kind of strictly increasing. So if there was a question that relates that how many real roots this type of polynomial might have. So let's say how many real roots. So then you know that there is exactly one, because since it is strictly increasing, so let's say, so let's say this is kind of strictly increasing like this. So since it is strictly increasing from R to R, there is only one time that it is going to hit the x-axis. So these are the types of things like smart applications that you can actually do with this first derivative test, which you have done before as well. So what happens is, suppose if I give you a sequence like this, n x square by n plus x square, n square plus x square. So suppose it's a sequence given like this. This is your fn of x, and there are some properties that has been given to you, and you are trying to establish some facts. So then, is this sequence of function increasing or decreasing, that you can actually, or let's say for the variable x. So in this scenario, it is sufficient if you check fn plus 1 minus fn. But suppose for this type of functions, you needed to check the increasingness or decreasingness, then you go for the first derivative tests, where you know that the derivative will exist. Okay, so that's kind of what we have before the Taylor's theorem. So just before that, I will try to convey one theorem which is not that famous, but it is very helpful. That is Cauchy's mean value theorem. Okay, so what does Cauchy's mean value theorem tells us is that let f g be continuous on closed interval a comma b, okay, and differentiable at open interval a comma, both of them. Okay, so let g prime of x is not equals to 0 for all x in a comma b. Then there exists a c in a comma b such that f of b minus f of a by g of b minus g of a is equals to f prime of c by g prime of c. So why is this important is because some of the problems of this form, as you have seen. So if you have a function of this form, okay, like, then you can actually use Cauchy's mean value theorem to understand what f prime by g prime looks like. You don't have to compute at a certain point, of course. You don't have to compute it again and again to make sure what it is. All right. So after this, we are left with the Taylor series expansion. Now, the Taylor series expansion, it practically has one form. Okay, so I will just write down the Taylor's theorem, and it is practically used in series computations and stuff like that. So Taylor's theorem, let n belongs to n, and I is always my a comma b, and let f from I to r be such that f and its derivatives f prime, f double prime, dot 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 dot, if n are continuous on I, and that if n plus 1 exists on a comma b. So now if x naught belongs to I, then for any x in I, there exists a point in C between x and x naught, such that you have the Taylor's expansion. That is, f of x equals to f of x naught plus f prime of x naught into x minus x naught, and it goes on like this, as you know, x naught by 2 factorial x minus x naught whole square plus dot 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 dot, dot plus f n plus 1 c by n plus 1 factorial x minus x naught n plus 1. So this is the theorem that we all know about. Now the applications of Taylor's theorem is, I mean, it's huge. In syllabus of IIT JAM, there is not that much given, but I would request you to go through the Bartley-Schurbert's convex function chapter. Convex functions. Okay, so it's in the page 187. So if you go to the convex function, you will certainly realize that how in the proof of the convex function Taylor series are getting used. All right. So in differentiation from real analysis, solely from differentiation, you don't need anything else that much. It's just mainly it is mean value theorem and Darbox theorem. Okay, those two are the main thing. So it is requested that you go through those just before going into the exam. All right, and how you use mean value theorem and see some typical problems from IIT JAM and stuff like that. Okay, so after differentiation, we have the Riemann integral portion. Now, from the Riemann integral portion in IIT JAM, what you actually need are these things. Integration. So if you look at the syllabus, they have written that properties of definite and indefinite integral. So that is the first thing. Properties of definite and indefinite integrals. Okay. So what do I mean by, so mainly properties of definite integrals. Okay. So what do I mean by properties? So these are all +2 level properties that you have learned. So if you have ever prepared for JEE mains and stuff like that, you pick a book of that and go through the properties of definite integrals. So just like this, that if you have I equals to some minus a to a of f of x dx. Then if f is even or odd, depending on that, you will have 2a or 0 to 2a or kind of 0 to a, right? So those type of properties, all those plus 2 level properties, you just give it a go before Riemann integration. All right. The next thing of Riemann integration is the upper and lower sum. So pictorially, what upper and lower sum is, so suppose if I take this graph, the first thing Riemann integration does is that break this interval into small grid lines. Okay, so it is a uniform small grid line. All right, so let me draw these up. So it's like this. Now, what is the lower sum? The lower sum is you take from this interval what is the least value that the function is taking. In this case, the least value the function is taking in this interval is this yellow dot. So then you join this rectangle. For this, this is the least value, and you join all these rectangles up. Okay. So what you are actually doing, you are, so let's call these as xi plus 1 xi, these closed intervals. So colors here will dictate what am I actually talking about. So in this close, if you take this, so how do you take the area of this small yellow square? The area of this small yellow square is infimum of f in this neighborhood xi comma xi plus 1 into xi plus 1 minus xi. That's exactly what we are doing. Do you see that? Because infimum of if from xi to xi plus 1, that is nothing but f of xi. So if in this case, this is the area of this yellow rectangle, and that is how we are going to cover all these rectangles that are below the surface. So that is the reason that the lower sum is practically written like this: infimum at each xi plus 1 comma xi. So small n means infimum into xi plus 1 minus xi, where I equals to whatever you take, 0 to n or 1 to n plus 1, I mean whatever the things. So that is how this is the lower sum. Now what is the upper sum? So the upper sum is going to be the supremum. So what you are going to do, you are taking these rectangles for upper sums. Okay, so the blue ones are the upper sums. So this entire blue region is the is one of the areas in the upper sum. So that is why the upper sum becomes summation over supremum of the functional value into xi plus 1 minus xi. Now when the function is integrable, when you have UPF, so this is actually called as upper sum is with the partition of the function minus LPF, this is less than epsilon. That means that is when the function is integrable. So that's the basic Riemann integration without going into too much detail. Now one of the things that you need to like brush up, that when are the functions Riemann integrable. So it's safe to assume, if I just write down these, all of them will be integrable. First is monotone. functions. If a function is monotone, then it is integrable. Second, continuous functions. If it is continuous, then it is integrable. Third, of course, differentiable functions. If it is differentiable, then the first, the fundamental theorem of calculus, you can actually point out the Riemann integral. So these are the main three functions that can be Riemann integrable. So if in question paper, if you find that a function is given fx and will it be Riemann integrable, if this is the function, oftentimes you can kind of make sure it is Riemann integrable by making sure if this function is monotone, continuous, or differentiable. Oftentimes, but I'm not saying that these are the only things. The interesting part of a function being Riemann integrability is that discontinuity at countably many points. Okay, so if a function is discontinuous at countably many points, then the function is always integrable. All right, so this is very important. So it's better if you go back and take some notes, try to figure out some problems where this is the case. Okay, so apart from this the key point in Riemann integrability is to determine the easiest partition. So what is the partition? That is the grid that we are actually making in the x-axis from A to B. So Riemann integration is irrespective of the choice of partition. That is the reason you need to be able to figure out what is the easiest partition. So let's say if you have 0 to 1, all right, so then you start with 0. Okay, so you start with 0 and you take 1 by n kind of. So you are not starting with 0, you're starting with 1 and then you take 1 by n. So then at n tends to infinity, it is going to 0. Okay, so in generally, how do we do that? So suppose if you take 0 and then you take 1 minus 1 by n. So then at n tends to infinity, it is going to 1. Okay, so these type of partitions are actually needed for like cancelling some things out, because at the end of the day, if you look at the summations of both, so both these summations are of this form, xi plus 1 minus xi. So this is the lower sum and the upper sums are actually m into xi plus 1 minus xi. So this will always be there. So the first thing is x1 minus x0 plus m into x2 minus x1. So these cyclotomic things will always come. Okay, so that is the reason to choose the easiest partition is something that you should be very careful about, because if you take very difficult partition, you might get the answer, but it might take a lot of time. All right. So now to top it off, if you have this, let's say if fx is given differentiable like this, phi1 x, phi2 x, f of t dt. So then f prime of x is f of phi2 of x into phi2 prime of x minus f of phi1 x into phi1 prime of x. Always remember this Leibniz rule. So this is actually Leibniz rule, which is very helpful when you need to use L'Hospital in integration situations. All right. So I'm talking about something like this. Let's say limit x tends to 1, 1 by x minus 1, and then this type of integration is given. So then it is 0. Okay. So how do you treat this? So this function you treat it like this: integration by x minus 1. Okay. So now if you look at it, that if you put at 1, so x tends to 1, then if the limit is also going to 0, then you are in a inhospitable situation. Okay, because you need to figure out that what happens if you have limit at the integral portion. So whenever you have, so these are tricks, these are not conceptually solid things. I'm not talking about conceptually solid mathematical, let's say, theorems and stuff like that. This is how you get to understand what to do. Okay, so suppose at, if you put x equals to 1, the integration becomes 0. So this is now in 0 by 0 formulation. So what you do is you take the derivative of this and the derivative of this and then put limit x tends to 1. So then that will be your limit. Okay, so I think that's all in the real analysis portion for IIT JAM. So hopefully these two videos might help you to look for certain things before going into the exam. We will have a problem solving session on real analysis of IIT JAM problems in this upcoming Saturday. So, okay, so till then, I think goodbye and stay safe in this COVID situation. So, yeah, that's it for today. If you have any questions, so let me see what are the questions. There are some problems where a functional equation is given and they want us to deduce some facts about continuity. A functional equation, so that actually depends on which type of functional equations you have. So let's say if you have been given a functional equation, so let's say like this. Let me uh, quickly give an example. So you need to figure out the problem child. So problem child means what is the problem. So suppose these type of functions are given. Let's say x sine 1 by x 0. So when x is not equals to 0, when x is 0. Okay. So suppose you want to figure out the continuity. So I hope that this is the type of problem that you're talking about. Okay. So if you have x sine 1 by x and fx equals to 0. So see, x sine 1 by x, if x is not equals to 0, this is a power series. Hence continuous. Okay, so this is a power series, hence continuous. So the only problem for this function to be continuous on entire R depends on checking continuity at this x equals to 0. So whenever given a functional equation, so let's say given a functional equation, to check whether it is continuous or not, we need to figure out the problem points. So where there is a problem for that function not being continuous, and generally it's kind of always like in these type of boundary cases. Okay, so then after picking out these problem points, what you do is you simply check, does this hold? So just like this, in this scenario, if you look at this, so then what you are doing, you are taking x tends to 0, x sine 1 by x. So you are trying to understand if this is equals to 0 or not. Now by sandwich theorem, this is 0 because like x sine 1 by x is less than equals to x and greater than equals to minus x. So both of these by sandwich theorem goes to 0 at limit n tends to infinity at x tends to 0. So then this will go to 0 as well. So these are the types that you can actually think about. Okay, so yeah, that's the question that you have in mind. Like there are no specific ways. Different functional equations requires different type of treatments, but in general speaking, you need to figure out what are the points where there is a kind of like where you are not sure that this function will be continuous or not. Then you just use the definition of continuous. Okay, then so if you guys have no more questions, then let's wrap it up. So lastly, I'm going to ask, is there any question? Okay, fine. So if not, then thank you for joining. We will meet with some of the problem solving sessions in the upcoming session.